So firstly, let me introduce myself. I'm Anit, and now we are back. Our next speaker is Ved Prakesh, staff data engineer at GitLab. He will guide us through setting up Iceberg tables in Snowflake, covering everything from the basic to advanced features like schema evolution and time travel. Yes, Mr. Ved, the mic is with you.
Yeah, thank you. Hi, good morning, everyone. So this is, hope you're able to see the slides. If not, please let me know. I'm just playing around with the slides. So welcome to this setting up Iceberg tables in a Snowflake, basic to advanced technique tutorial. Very happy to be here. So just want to share what I have learned. It's not like I'm the best expert in the market, but this is what I'm learning and what I have evolved in the course of time as part of my job. And this, just a small disclaimer: all this information is pertinent to me. It's not GitLab as a company is not. So I work at GitLab. So just wanted to call out this. Scan the QR code if you're interested. This will take you to my LinkedIn profile, but just about something about me. So as a staff data engineer with over 15 years of experience, I'm passionate about leveraging data to drive business insights and create innovation solution. My expertise spans around GCP, AWS, Snowflake, primarily Python, PySpark, Terraform, dbt, uh, Monte Carlo. But currently, in the last 1 year, what I have been working on is like basically on the Snowplow, Dataproc, and Apache Iceberg, basically to implement data observability tools, along with building a much more complex and highly scalable pipeline where we are getting an abundance of data coming through from our CDC pipeline. So with this, let's look forward what's next. So what you will learn today on the terms of, so we'll get to understanding of how Iceberg as a table format, setting up and working with Iceberg in Snowflake. I have prepared a lab, but somehow my something I have messed up over there. So I will share the repo link where you will have all the steps by end of the day. It should be with you, but even after the session, we will try to go through the lab together. I have done most of the settings, but I think somewhere I have messed up the access control. So we'll go through that. Optimizing, we'll discuss about optimization for performance and maintainability, advanced feature for real world scenarios, and troubleshooting common issues. With this, I would briefly about to walk through as a company, or the GitLab as a company. So GitLab mission is for everyone can contribute, reflects our belief that innovations thrives when barriers to participations are removed and every voice has the opportunity to shape the future. So by building the both our product and our company culture around transparency, collaboration, and inclusion, we are creating an environment where diverse perspective converges to solve complex problem, resulting in better software and more resilient organization that can rapidly adapt in increasingly digital world. One more slides, two more, and then yeah. So GitLab has a credit values, and this thing what you see on the screen, where collaboration are for results for customer efficiency, diversity, iteration, and transparency. These are the GitLab values with which we as a company survive through. We make better product every day. We make things good. So we see the collaboration where we believe that the people work together across boundaries, sharing knowledge openly and combining their unique perspective helps us to make a better solutions. No single individual could develop alone. So it's always a collaboration. Result for customers is we focus on measurable outcomes that delivers real value to our customers. Efficiency, we pursue sustainable productivity by working smarter, automating where possible, eliminating bureaucracy, and being mindful of both our time and others. Our diversity, inclusion, and belonging. That's very crucial as well. We've committed to building a company where people from all backgrounds. So that's where we have people from across the globe, people across the time zone working together to do it. We believe in iteration, starting small and improving continuously. So we iterate faster, which help us to deliver faster. And TS stands for transparency, as you all understand. Transparency by documentations, repos, as that's why most of the GitLab repos, what we develop is mostly public, which can be used for the future reference. What GitLab is doing. Uh, this is a question, right? So the GitLab is a DevSecOps platform delivered as a single application, unifies historically separated development, security, and operations tools into one coherent ecosystem, eliminating integration headaches, communication silos that typically slow down teams. By bringing the entire software lifecycle under one interface with shared data and consistent workflows, team can collaborate more effectively, address security concerns earlier. So this helps. This is what GitLab is, and a little bit about a data platform team where which the team which I come from. So it's a part of the central data team, and the central data team basically works in the hub and spoke model, where as a data team we are one of the. If you see on the far right, we are the data platform team. I'm part of the data platform team, but we serve our counterparts in analytics engineering, enterprise insights, and a data science team. But we also serve to the business domain. Like we have, as a whole data team, we serve to the sales and marketing, product engineering, finance, people ops, to all. And data as a data platform team, primarily or we are primarily responsible for reliable, scalable, and data platform and ingesting the data. So with this, we have a little past about the GitLab. Now it's time to dive deeper. And what's the modern data challenges, right? Petabyte scale analytics, real-time access to data. That's the need every time people want just as much as possible. Schema flexibility without chaos, multi-engine processing, cost efficiency at scale. So with as the data is increasing, as the things are increasing, there is always a need to have cheaper solution which is scalable, so we don't pay a lot for the same thing. So if we look on the image, like 90% of data team is struggling on scaling traditional data warehouses uh, to a modern approaches, trying to solve the volumes and the velocity in the parallel. And so basically traditional approaches often faces trade-offs between reliability, performance, and flexibility. So with this is like the scale of the data, that I think that's the biggest thing, the reason to have like a solution like an Iceberg or Delta Lakes or Apache Hudi, where you have like open table format, your uh, what you can this can scale as much as you want. Real-time access to data, that's pretty much possible. Multi-engine processing, like you can talk to from different systems like BigQuery, Trino, Presto, Databricks itself for a Delta Lake example. So moving towards evolution of data storage. So let's look at this diagram and see what's the traditional databases. They had like schema enforcement, they were ACID compliance. ACID compliance stands for the atomicity, consistency, isolation, and durability. Uh, Limited scaling. So these were the very good thing for the traditional, but there was a drawbacks, right? Limited scaling. You can't scale more than that. You have a Oracle instance or MySQL instance can scale to a limit, then it starts giving performance issue. High cost at a scale. So the bigger the machine, the more you pay, and it is a kind of a vendor lock-in. So if you are using Oracle, you're tied up with Oracle. If you're using MySQL, you're logged in with the MySQL. Then came data lakes, basically massive scalability, low storage cost like Hadoop. But the problem was schema challenges, no transactions management, so there was not an ACID compliance, management overhead, it requires lots of resources to manage that particular infrastructure. And then comes Apache Iceberg, right? So it had a schema enforcement. Basically, it was a mix of both traditional database and data lakes, where it has a schema enforcement and evolution. It had an ACID transaction, so it was ACID. It supports the atomicity, consistency, isolation, and durability of the record. Massive scalability. We can scale as much as we want, but we haven't tested like we're going above petabytes. But we can definitely go for a significant amount in petabytes. cost effective storage. So you use your cloud provider storage. So you don't use your vendor provider. So you can use like object storage like S3, GCS, Microsoft Azure, or you use your own file system where for it's an open format, so no lock-in. You are it's the files are stored in a columnar format, so it can be consumed by and you can re-extract it back. Multi-engine support, so it works with different engines like Trino, Presto, even with a different catalog for Snowflake. If you are using Hive, then you can use it for Hive Metasql, and it works with a BigQuery. So it's a free of this. So it can work with our Delta Lake. Also supports similarly. It goes for this. So they have Iceberg is a different variation if you comparison to Apache Hudi and uh, Delta Lake. So we will be focused on this for the Iceberg part. So why this matter? Why this matter in the sense real world impact? What's the benefit of having an iceberg as a solution? So let's take a case study for an e-commerce giant. Before icebergs, it used to take 8 hours of batch jobs. The schema changes took weeks, terabytes of wastage of storage because every time you modify a file in a Hadoop file system, it creates like it do not modify update the existing file, it starts creating a new one, and you it takes a lot of time to refresh the whole table. uh, all the files which were old now are wasted. After iceberg, basically it's all like 2 hours of processing time. It reduces the way the catalog system works. It makes it much more smart and efficient to do it. Same day schema updates. So if you're doing an update to the schemas, adding a columns, or which you will cover it later, we'll see through. And 40% of storage reduction. So there was a reduction in the storage. That's like significant because we update the tables, we update the records in the system. Looking at the case study for financial services, where it's a rigid data structure before Iceberg, limited history, slow compliance reporting. But with Iceberg, it became flexible evolution. 2 years of history, compliance queries in a minute. So it was fast to use. You can put up and with the Snowflake coming up, it helps a lot because you can use the Snowflake power to query your data setting in the Iceberg. With this, I would like to focus towards the agenda of the session, primarily towards introduction. So what we will be covering up. So we'll try to build a small foundation, introduction to Iceberg tables, why Iceberg, the benefit of basically setting up your Snowflake environment. I will try to walk up through, but I think the lab is not there. So this is the part we might have to skip, but I will share the whole repo with all the steps today so you all can follow through it and do it. And please reach out to me if that not work. Please comment on that. It's an open repository on GitLab, so you can create or you can create an issue, or if you needs more information, we can walk through that over there. We'll walk through the implementation and best practices, basically creating and managing a Snowflake managed Iceberg tables, working with external Iceberg tables, optimization techniques and problems, advanced features and troubleshooting. So the part 3 where we talk about changing without breaking, schema evaluation, time travel capabilities, common challenges as a solution. So what are Iceberg tables? Like we all are talking, right? So is it like a database? Is it like a query engine? What it is? So Iceberg is basically an open table format for huge analytics datasets that brings reliability with ACID transaction, performance at a scale, flexibility of evolution, vendor independence, designed to solve problems that arise when working with petabyte of scale. So let's take this example to understand a little bit low. So if you see Iceberg as a table, right, you have all books in your library is a one giant pile. So it's called a library analogy. Searching means looking through everything. So if you go to a library and it is just kept in a one pile where every books are there, then it will take you ages to find out a book which you are looking for. But if you had this cataloged, You know that where each book is. You know all the changes, like who has collected the book, who has returned it. So that's called a cataloging thing. Show a library as it was last week and find exactly what you need without disturbing everything. So that's what is Iceberg table. It helps you to know that where each record is setting. That's what is maintaining the catalog. It tracks all the changes, whatever is an insert has happened or update has happened or a delete has happened, where it is a, it maintains the state. And if when you query the table, when you try to look for the file or record, it gives you the exact record without disturbing a lot. Right. So that's how, or a very simple way to explain the iceberg table, uh, like what and what. So if you can assume that if you go to a library, basically iceberg table is a kind of a library solution where it has everything cataloged, everything known, that who has borrowed the book, who has returned the book. You know that uh, when will be the, what was the history of a particular book when it was issued, so you're able to track the changes. If a new book has been added, you know that this book has been added. And when you start looking for a data, or you start looking for a particular book, similarly, if you start looking for a table or a column, you will be able to look at inside in their catalog, and you will get that without knowing, without having to scramble through all the shelves and everything in the book. So why choose iceberg? So what is the benefit, right? What's the benefit? Why to choose an iceberg? So schema evaluation. I think that these are the like the top 5 things which comes up to the mind. So if you add or modify columns without downtime, it works. Time travel, you can query historical data using snapshots. So that's something is quite good, because a Snowflake is used for time travel, where you can query, if you set up a latency of like 90 days or time retention period for 90 days, you can query any update deletes happening on a particular permanent table to 90 days back, right? Performance, fast query with metadata based filtering, so we can, performance is great. Consistency, because of the ACID transaction for data lakes, that works. And partition evolution, changing partition without rewriting the data. So these are the top 5 things, the benefit which comes up with the iceberg. Now looking at the classic data lake problem. So without iceberg, the file level management is complex, no schema enforcement, slow metadata operations, limited concurrency, and no consistency guaranteed. And when it comes to the iceberg, we have table level abstraction, schema enforcement and evolution, fast optimized metadata, high concurrency, and async transaction. So in the simple example, why iceberg win? What's the difference? So one handle growth and changes gracefully, but the other breaks when adding a new column. So basically, when you add iceberg, when you add a new column to the iceberg, it can handle this change very gracefully. But when you add to a other data lake system like Hadoop and all, adding new column is a nightmare. Changing column types, if you want to change the column type from varchar to integer, or to a double from integer to decimal, like that, it's a nightmare in the old system. It works. So Iceberg handles this pretty smoothly. Evolving partition strategy, handling concurrent writers. If you want to do a multiple writes, it's much more simpler and controlled way in Iceberg in comparison to other traditional data lake solution present in the market. So if we have to like this, then we need to understand like what's the Iceberg architecture look like. We talked about meta files, we talked about, so what keeps it different from the other solution? So if we say the Iceberg architecture, it has 3 core component. One is the data file where your actual data lives, typically Parquet format. I believe Iceberg also supports ORC, but I have not used it, so I wrote Parquet over here. So the data files where the actual data sets, there is no, it's stored in a columnar format. It's just and highly compressed, so the data looks good. There is a recommendation like to have it like a compressed like 200 to 250 MB, something like that, not a bigger file size, which we'll go through a little later. The metadata files, it contains of two things: manifest files, which is the basically contains the list of data files with detailed metadata and statistics, and the metadata file itself, which is basically a top level references that track the table history. So with this, this structure creates just a like just right level of abstraction, not to result like traditional databases tables, but not too chaotic like a raw files in a data lake, right? So you have a file which is safe, but you have a metadata, and that's what the manifest file plus the metadata files collectively forms the metadata. So when you look at a file, when you do the lab, and when you will be doing it, when I say you in the S3 bucket or in the cloud storage, you will be seeing two folders. One is called meta and one is called data. The data has the actual file sitting over there, and the metadata contains this manifest and the metadata information. So metadata file hierarchy. So a little bit we have to go into the metadata file hierarchy to understand. So snapshot, point in time view of the table. This layered architecture enables Iceberg powerful features. Manifest list, a reference to all the manifest files. Manifest files, list of data files with the statistics and data files, actual data in the bucket. So if you put it in like in a hierarchy, the snapshot comes to the top, manifest list, which contains the information about all the manifest files, which is referencing to that. And the manifest file itself contains the list of data files with the statistics, with the range, with the all the other important information, what is required to identify a particular row inside the data file itself. And when we talk about Iceberg, we talk about one thing which is very common. This metadata and the data is just the way the data is stored. But in order to access or even in order to like query or to use this, we have to use something called catalog. And it's quite used, it's quite verbally known. Everyone talks about catalog. So what's a catalog? So basically, catalog is a stores the metadata about Iceberg tables like schema, locations, and version. So the metadata which sits, if you split the file, if you look at the way the Iceberg creates the table, it creates a data file and a meta file folder separate. This catalogs works on that meta directory, the meta folder. It picks up that stores, and it's this catalog is the way using which you write the data to Iceberg and you read the data from the Iceberg open table, right? So this is their way of entry. Without a catalog, you will not be having any Iceberg thing. So it's always comes with a catalog. It can be a Hadoop catalog, it can be a REST-based catalog, it can be a Hive meta store, it can be anything, but yes, you need to have a catalog. Like the schema, locations, and versions help you register, discover loaded Iceberg tables. And basically it is acts like your directory of tables, similar to how a database has a schema and a list of tables. So when you query Iceberg, you basically query the Iceberg table through the catalog, and it behaves like basically saying that, okay, this is the database. It gives you a seamless integration to your open table, to your table sitting, data sitting in the storage layer, by just saying it gives you like, okay, this is the database, this is the tables, this is the columns, that's, and you can query everything like a simple SQL database. So a catalog is basically, if you look in our librarian terms, what we were talking about, the analogy about that, it tracks or where all the tables are located, know what format they are in, maintains the metadata that describe a structure, records the history of the changes. Without a catalog, you would have no idea what's in your data lake or how to find it. It's the same problem like a library, right? Without a system in place, without a catalog present in the place, you will never be knowing where is the particular book sitting and how do I need to find it now, because then it will be a complete book of piles, or books of piles, right? So that do not help a lot. So that's why a catalog is a very important thing in the Snowflake. Which catalog you choose depends upon what query engine you want to intend. There is a catalog like Hadoop catalog which works with the Trino, which is formerly known as a Presto query engine. There are catalog which works with Tabular IO, who is a catalog which works with a Databricks. Then you have Hive Metastore, I think, believe so. That works with the Google BigQuery. Then you have an open catalog which comes from Snowflake. Basically, it's called the open source version is called Polaris catalog, and this is a REST-based catalog where you have to make a REST call to update your catalog and all. This the beauty of this open catalog is that it can work with multiple different engines. So the major limitation right now with cataloging solution is that the Hadoop catalog or those other catalog tabular can work only with one or two query engines. But with REST catalog like Polaris catalog and the Snowflake named called Open Catalog is something you can work with multiple engines. So if you're using REST catalog, it can work with Hadoop. Sorry, it can work with BigQuery, it can work with Trino, it can work with Delta Lake, it can work with Snowflake. So that's the behind the you need to be very much cautious when you start to selecting that which catalog you want to use. You can use a normal Hadoop catalog for your local file system development. It's perfectly fine. But when you try to look it at a scale and for production, you need to see that which one is most viable, which fits your use cases. So if look at what is a Snowflake, right? We're talking about just a little. So basically, a Snowflake is a centralized data storage and analysis system. Basically, it is the place. It's a cloud-based solution for the data warehouse, where we have three layers where the storage is separate from compute and the compute is separate from the remaining of the service layer, which is manage the administration on a particular database. And it's basically this, it's a scalable storage compute and separate processing layer, support complex queries and machine learning workflow. Okay. So if we move further and we move towards in the direction towards like a Snowflake plus Apache Iceberg, right? Snowflake is a proprietary solution, is a proprietary, like it's a not an open source, but Apache Iceberg is an open source solution. So this is very combining a Snowflake robust engine with Iceberg open format. I believe you get the best of the both worlds, high performance and flexibility. It allows how do you say a hybrid cloud and a multi-region, multi-engine access to the same data. So as I was explaining earlier that if you are using a Snowflake open catalog, then it can work with a different engine at the same point. It can work with Spark, it can work with Trino, it can work with Google BigQuery, it can work with Databricks. Google BigQuery, I need to still validate, but it works with the other query engines. It allows basically to have a hybrid cloud. So you have your Snowflake sitting in AWS and you have your Iceberg data sitting in GCS. So that makes your like you can don't want your data to leave you want to do the heavy processing where very close to the source of the data. I think this is something which helps. You otherwise you have to move everything inside a Snowflake and then do a heavy transformation. I think that will be uh, the same traditionally we hit up the same problem of loading this petabyte of data into. So what makes so it we have the open and flexible table format. You can query with a Snowflake SQL engine. That helps a lot, right? Because you don't have to build, maintain an additional layer of your own query engine. We have with the Snowflake interface itself, you can manage the time travel and rollback features. That is coming as default in the Iceberg, but it works very smoothly with within the Snowflake interface. We can manage that much more easily. Seamless data sharing and compute storage separation. So you want to share your data between, like you are keeping your data in Iceberg, but you want to share it with people of Snowflake, like a customer of Snowflake. And it's much more easy to bring that data from Iceberg. You can create a view on top of it, if it is just one table or something, or materialized view on top of it, and then you can share that secure materialized view to your partner, or within even within the department, within the same organization. If you have a different Snowflake account, you can share that data. And having this storage and compute separate, you can run a better what do you say interface on this, and basically you get a much more better performance, because your write can have a different warehouse and you can have a read can be having a different warehouse. So that helps a lot in order to gain this flexibility. The next slide is a lab, but basically in this one, which I have, my idea was to cover to create an external volume, define Iceberg table, insert query data, and a snapshot and time travel features. I think this is something which I was working upon. It unfortunately, this lab got messed up. I will have to send this to you after this call. Need to fix few things, and I don't want to show a lab which is not working. I've just before this, Sachin, I did something which broke the what do you say my integration with AWS. So I will have to skip this. Sorry about this. Apologies for this one. But I will share the lab which you can do it when you do it. It's a step by step. It was a very clear instructions. It comes with all the snapshots and required script which you can do. One thing, if you want, you need to do this. You need to have for this lab an AWS account, which is of a free trial. It works perfectly good. You need to have a Snowflake account, which comes for a 30-day trial. So you can just log into Snowflake and fill in those environment where you want to. Choose AWS as your cloud provider, from where you want to host the Snowflake, and whichever reason you choose the AWS for the what is it for the cloud provider for hosting the AWS. In the same reason, you ensure that when you go to AWS to create the S3 bucket and all, you host it in the same region. You create that everything in the same region. So with this, we'll move towards to the next part of the agenda. Is basically the best practices to be followed for this, and what would be so to be here. So partition strategies for Iceberg table, right? So if you look that there is has to be like a very well thoughtful partition strategy when you are building the Iceberg table, because it helps you to drive the query partitioning. So so when you think of this partition, always partition based on the column commonly used in where clause to enable partition pruning and dynamically improve query performance. So that something has to. So when you build the table in this Iceberg, you have an option to define the partition. And in a Snowflake, we call it clustering key, like where you can define a clustering key on which you want to cluster the table, so that it is much more. And similar to Snowflake, in Iceberg, you can look for look at your examples or the queries which you are planning to use. Set is used in the where clause, which will help us to, if you have suppose like a 1 terabyte of data, and it has a lots of like 100,000 of small file inside it, you don't want to read all 100,000 of the file. If you have defined like I want to just look for data for this particular region, so in those 100,000 files, maybe there are 200 uh, 2,000 files or 20,000 files which has data for that particular reason what you're after. Not all of them are there. So if you define while creating the table, you say that partition it based on the region, then it is very much easy, and that's the very first filter within your where clause and in the joins, that I want everything from this region. Then Iceberg, the cataloging solution, when it hits the query hits, it reads through the catalog and it picks up only those 20,000 or 2,000 files which has the information of that particular region, and it don't go through all the other files. That gives the major benefit of performance. Another topic or thing which we need to think, use transformation, month, year for dates. So for date and timestamp column, use transformation like year, month, or date trunk rather than partitioning on raw values to create logical grouping and prevent excessive partitioning. So suppose you say that, okay, I want to have you have a transaction timestamp, for example, as a value coming in your transaction file, then don't partition on the timestamp, okay, or don't partition on the date. So you do it on basically year. You abstract the value out of that transaction date and make it year, month, or date trunk. So just keep the date, don't use the timestamp. So that will reduce the number of partition, but it will also keep it very much intact. Do partition size balance. That's something. Aim for partition size between 1 GB to 10 GB. Too small causes metadata overhead. Too large prevent effective pruning. So that's something we need to be taking care of. But that comes when you hit that scale. So once you start seeing a problem, you need to start looking at, is this a partition? And that's something we discuss, like how do we troubleshoot the performance? And that's sizing. This partitioning makes a major role when we play that. Cardinality control. So avoid choose columns with appropriate cardinalities, hundreds or thousands of unique values, not millions, to prevent Cartesian explosion. For complex scenario, use Iceberg hidden partitioning to separate physical organization from logical representation when a standard partitioning would be too restrictive. Leverage Iceberg ability to change partitioning schemes without full table rewrites when query the challenge. Multi-level partitioning, that's something is applicable to the table which is more than 100 terabyte. Consider doing a multi-level partitioning by year, then month. Basically, the way you store the file, you need to store it like year, month, date. Create the hierarchy that improves filtration precision. Uh, Ensure relatively every distribution across partition to prevent hotspots and optimized parallel processing. Test before production. That's not to be said, but yes, please validate partitioning strategy with your respective queries before implementing in production and adjust if it is required to be done. The next thing is, which we look into the best practices, is the file size optimization. As said, right, too small files under 100 MB create excessive metadata overhead because you don't want to have your metadata itself of like terabytes and petabytes, then it will not be useful. So increased management complexity results in poor read performance due to high startup to processing time ratio. Too large files over 1 GB reduces parallelism, limit effective resource utilization across your cluster, and can cause memory pressure when processing individual files. The just right size is 128 MB to 512 MB. This is like a sweet spot. The balanced metadata efficiency with optimal parallelism, efficient compression, and enable effective data skipping filters. So we're typically improving query performance by 3 to 5 times compared to the poorly sized files. If your size is too small or if it is too big, if you rewrite those files, rewrite that partitioning by creating a new table with a partition on date, year, suppose after 100 terabyte, and all the solution which I suggested in the previous one to have like a multi-level partitioning, that this putting this partitioning file size within this open table format for this between the 128 MB to 512, it helps a lot. I would say even not this something which was I picked it from their website, but I would say having it between the 256 MB to 512 MB, I think that's the much more sweetest spot. That's what I am doing. So that's a suggestion which you can take. So next in this is like basically we are moving towards the phase 3 of this session, and that's advanced features and troubleshooting. And in this we'll cover something which is what are the advanced features which is present in the Iceberg, how do we troubleshoot it, and the same. So a schema evolution, changing without breaking. What does it say? It means that suppose you have a table which has three columns in it, and you wanted to add a fourth column. In the old world, it used to be like literally lots of issues in order to update this whole file system or behind the system. So schema evolution is one of the most powerful features of the Iceberg. It makes database changes non-event instead of dreaded migration. So it is not like we have to migrate now the data from this files to another file because they have added a new column or a change the data type. If you look at the queries which are over there, if you need to like alter the customer data and add a column, you just add it and it just takes effect. Similarly, it's similar to like a normal table in a Snowflake. It does that. You rename a column or you want to change the data type there. So Iceberg table enables seamless schema change without downtime and data migration. Adding a columns, modifying data types, or rename fields while maintaining backward compatibility with existing queries. I think that's something is really uh, groundbreaking, I would say. This eliminates traditional pain, right? So that's the idea behind having a strong schema evolution. Then that's something which is coming, and it helps to like historical schema version, so you can still maintain the history because it maintains the history, allowing different clients to smoothly transition at their own pace. The next thing which is coming up is the time travel capabilities, right? Iceberg time travel allows querying data as it existed at any point in time, enabling audit trails that precisely track who changed, what, and when. So this is like point in time reporting for consistent historical analytics, a rapid recovery from accidental data modifications or deletion without restoring backups. This powerful features of the time travel basically helps to transform data governance from a painful compliance exercise into seamless capability, giving organization the confidence to quickly correct mistakes while maintaining complete visibility into their data history. So this, if you look at the query again, this I've given a sample query. You can look like within a Snowflake, you can run like at and offset -2. It takes you like 2 minutes before. If you want to look for a timestamp, which at timestamp, what was the data present in the particular table, it is possible in Iceberg to do it. And it is much more easier and smooth to do it from a Snowflake because these are a Snowflake related queries. So you don't have to go and learn the syntax how the Iceberg will work on a particular query engine. If you know Snowflake and normal, all the syntax for a Snowflake, this works very well for the Iceberg table in the Snowflake as well. The next thing on this capabilities comes the Iceberg versioning and history. So Iceberg maintain a complete lineage of every table modification through immutable snapshots. It takes a snapshot, creating a rich versioning system that tracks all the changes from creation through the table's entire life cycle. Isn't that good, right? You used to maintain version in a Git repository or a GitLab where what has changed, what has not changed. With this immutable snapshots, what Iceberg is taking, you can maintain the history of your table, the what has changed from what, and you can maintain it as long as you want based on your business requirement or a compliance reason that I want to maintain a 3 years of history or a 4 years of history. You can maintain that. It's a very powerful tool to do this. This versioning foundation helps powers Iceberg's most valuable features from time travel and rollback to incremental processing, reproducible queries by preserving the exact state of data at each transaction, allowing teams to confidently access consistent historical views without the complexity of traditional backup and restore operation. So this is literally like a groundbreaking thing which helps to do. Right. Sorry about that. So moving to the next on this, we will be moving further, and that would be the last part, like the troubleshooting part of the slow query performance. When Iceberg query underperform, the most common culprit are ineffective partition pruning, suboptimal file size, missing or outdated statistics, issues that can be quickly diagnosed with Snowflake performing analysis tools. The solution typically involves strategic adjustment, like rewriting small files into large ones, updating table statistics with analyze, redefining partition strategies to better match query patterns, or implementing a data clustering that aligns with frequently joined columns. Interventions that can often transform slow queries into performant ones without changing application code. So these one topic about the slow query performance, if you look at that, it covers the small size. We should be very much cautious of the size what we are writing. If the size becomes too big, that's a problem. And the partition what we defined, because partitioning is very crucial to know that how much big the file size is getting generated. Okay, if you see that your table has not working perfect, performing very well, and is going to a slow query performance, you can look for the rewrite of the file of that and look at the target file size, what has happened, and it can create do it for you. If we have to circle back and look like why have to go, then why Iceberg in a Snowflake matter? The reason is open table format, freedom from vendor lock-in. So your data is sitting outside Snowflake, you're not keeping it within Snowflake. You can point any query engine on top of it. So that's another thing. Fast queries, even at massive scale. So that's a really benefit. You can use the compute of the Snowflake to run fast and impressive query. Flexibility, schema evaluation without pain. That's something really flexible. So you don't have to worry about you're altering a table or you're altering a column or you are changing the data type or renaming a column. It works all good. ACID transaction for database, so that helps the reliability and interoperability, which is multi-engine access to the same data. This helps to this brings to the basically the end of the presentation. I have some information. If you need to have look at like official documentation, then we have a Snowflake Iceberg documentation which you can look for. There is Apache Iceberg documentation on their website. You can join their community, which is very active on GitHub, and you can also join the Iceberg Slack channel where you can ask all the questions and all the best practices what to follow. I have learned a lot from there. Been doing this. I'm still very sorry about the lab, which I have not able to prepare and show you the live demo that how this everything is working. I was very much hoping that that should be working. It was very small, easy thing, but I think I have done something. So this brings to the end. Again, this is me. If you have any questions around Iceberg or Snowflake or how I have set it up and how do we really make it work in the live, uh, this point of time, that's a work in progress, but within the next or 2 weeks, that will be a real life production thing which is running. So this is a QR code. You can reach out to me, find me, ping me, and ask me in questions on LinkedIn. I'm very vibrantly active over there, and I work very close to the Snowflake. So any query around when a Snowflake is formally welcome, and we can proceed for this. I will open the floor for question and answer because as per the my lab has been missing. So yeah, sorry about that, but yes, thank you. Hi, Yusuf.
Yes, hello
Hi.
there.
Yeah. No.
Yes. Okay, perfect. So since you are done, Does
Yeah,
anyone
my
have any
lab didn't
questions?
work, so sorry about that. I am literally, so sorry for that. But yes, any question
You're
I am
totally fine.
answer. Yeah.
Perfect. So, does any one of the attendees has any question regarding anything that Mr. Prakesh just said?
I have given in the chat the lab where it will be posted up. So this is the link where you can look for the information at the end of the day, where you'll have all the lab information coming up. So please save this, bookmark this particular URL, and this is where it will be present.
Okay, thank you so much for that, Mr. Prakesh, and thank you for that very fruitful session. Which really appreciate such a session, and I believe that none of the passengers has any questions so far. So yeah, I'm pretty sure this is everything. So thank you so much, Mr. Ved, once again,
No
and
worries. Thank you. Thanks a
yeah.
lot. Thanks for having. It was great.
Yeah, well, actually, your presentation, everything, the delivery, everything was pretty good. I really like the idea of the iceberg. So thank you so much. It was very fruitful.
Thank you. Please reach out if you have any more questions. I am on actively present on LinkedIn, so and there will be more
Perfect,
coming on Iceberg from my side. So you'll be there.
perfect, Mr. Prakash. And yeah, I believe this is gonna be a time for a coffee break,
Yeah.
and we're just gonna start our next session by 1:30. Thank you.
Thank you. Thanks a lot. Thanks.
Goodbye.
Bye.
You have a good one.
Bye. Thank you.